As mentioned in the previous tutorial, this video is all about vehicle engine sound effects. We have also prepared a small demo to show you how our sound system can easily be integrated with the default Chaos vehicle movement component of Unreal 5. Before doing a drive test, let's look at our engine graph. This part here is just some simple attack decay nodes to simulate engine acceleration and changing gear. We use this to quickly test a graph without having to hook it to game logic. For now, I will connect this to the RPM input, then this to the throttle input. The star of the show is obviously this node, Vehicle Engine Synthesizer. This node follows a completely different approach compared to granular synthesis. In case you don't know, granular synthesis is the most popular method to simulate engine sounds. Games like Forza, Project Cars, and Need for Speed all use granular synthesis. It's quite easy to implement, but its results depend heavily on the quality of the recording. And unfortunately, recording vehicle sound effects isn't easy. I know a very good GDC talk about this topic. You can find the link in the description below. Basically, it usually requires a whole team of sound engineers to do the whole setup. Then you need an empty road to the record. Also, the driver needs to understand how to drive to create a good ramp-up sound. So the recording can be used in granular synthesis later. Actually, cars are still doable. Things, like tanks and planes, are more problematic. Recording alone can cost you a whole fortune. Even just buying from a third-party source can be very expensive. And because it depends heavily on the recording, granular synthesis isn't really good when dealing with out-of-range RPM. And it isn't good on nearly stable RPM too. I will show you this problem later. So the motivation when we build the synthesizer is to break away from the traditional approach. We don't want to depend too much on the recording. We study the spectrograms of various vehicles, including cars, motorbikes, and even chainsaws. To build this model and this one, we only need around 0.5 seconds of audio. Yet, the synthesized results can realistically simulate a very wide range of RPM. That's a lot of talking, so let's hear the final result before continuing. Start up, changing gear, in, one more, then throttle release. Aside from the models, some parameters here are also tuned based on our analysis. From the user's perspective, the most important thing is obviously RPM and idle RPM. Throttle input is the input value from the player controller, which is usually mapped to the up and down on the left analog tick. You will have to feed the RPM and throttle input from your game logic every tick. The setup is very simple. I will show a real example in C++ later. All other parameters will be set up by us when we model a vehicle. The number of pulses per revolution is based on the type of engine and its number of seconders. A 4-stroke, 8-seconder engine will fire 4 pulses per second. A 2-stroke engine, which is used mostly in motorbikes and chainsaws, with 2 seconders will fire 2 pulses per second. RPM variation noise factor controls how we make the output more noisy based on the changing speed of RPM. This is because when the engine is speeding up, it tends to create more noise. This should always be lower than 0.5, or else it sounds like you're putting a flute into the engine. Who knows, it might be good to create some sci-fi spaceship engine effect. The random period is how often we apply frequency and gain fluctuation to harmonic modals. It's scaled inversely with the RPM variation noise factor. F0, or base frequency fluctuation, is the range our base frequency can vary. This range is automatically increased for harmonic frequencies. The harmonic fluctuation scale will affect how we scale this range. A value of 1 means we're using the default scale. Min and max gain random % determine the random range of each modal gain. Though they are percentages, you can use a value greater than 1 here for more noise. But too much can make the output sound weird. Number of modal deceleration is how many modals will be used when the RPM suddenly drops, like when changing gear or when the player releases the throttle. This helps to reduce the exhaust sound. A value of 1 to 4 is usually good enough for this. And finally, these parameters are just the same as in our previous synthesizer. Now, this node is good for creating the unique engine pitches of each vehicle. But we still need to synthesize more noise from the exhaust pipe. So the output is mixed with a random noise generator and put into an impact external force synthesizer. This node also uses a modal object. We call it muffler here, because it does act like one. Fundamentally, this node will filter the force input based on the frequency, decay, and gain from our modals. It's like a comp filter, also known as source filter. Or, you might have heard about it, a convolution reverb. This node is extremely powerful, versatile, and as fast as playing a wave file. It can be used for a lot of sound effects. We will see it again in the car brake graph. Before passing the modal object into the input of this node, we use an impact modal low pass here. This is the node I told you about in the previous tutorial. Remember that a modal object stores many modals. Each modal has 3 parameters: gain, decay, and frequency. So what this node does is reduce the gain of each modal based on the distance between their frequency and the cutoff frequency. It's basically an ideal filter. Thus, it's extremely fast, accurate, and lightweight. It also only runs when its inputs are changed. So you can use this node freely without having to worry about performance, latency, memory, or phase corruption like traditional filters. As you can see, the cutoff frequency is changed based on the base frequency of our engine. We multiply it by 10 on acceleration to allow high pitches, and reduce it to 6 on deceleration. This makes the exhaust sound more realistic. By separating the noise like this, you can easily customize it to suit your game. For example, for stylized games with simplified car models, you can reduce or remove the noise. Okay, then, we simply mix the noise with our engine sound. We also add the braking effect here. This attack sustain node is used to smoothly change the gain between acceleration and deceleration. We also use the idle RPM to control the gain on idling. The final attack sustain node is used to control the gain when the graph is started and stopped. Let's also take a look at our braking graph. This part here is actually quite similar to the engine graph. Here, we use a fast chirp synthesizer to synthesize the main pitches. By the way, this node is around 2 times faster than the original node in linear mode, and 5 times faster when in exponent mode. It's because the original node bends the pitch on each sample, while this node bends the pitch per block rate. Of course, the quality of pitch bending is lower, but it's considerably faster. Most of the time, the results sound very similar, so now it will be our default node for modal synthesizing. This node is used for the noisy part again. To make this sound like a real braking sound, the pitches are changed every 10 milliseconds. Another random pitch with a larger time step is also added here to make it sound even better. Also, the changing speed of the car is used to control the loudness and the pitches. So when the car is running really fast and the player starts braking, it'll be loud and have high pitches. Then the gain and the pitches will gradually reduce. We use stereo here to make it sound louder. For the car that the player controls, this will be enough. You will only want to make it wider on far away cars. The easiest way to make this wider is to add a delay to the left or right channel. Another less performance way is to use a stereo version of this force node. You will want to use another white noise generator here. The theory behind this is that when sounds reflect and come to your ears, they carry different noises and phases. Using both delay and this node will make it very wide. You can also add the Doppler effect for spatialization purposes. But it is out of the scope of this tutorial, so I will stop here. Let's start the demo now. First is a simple speeding up and changing gear test. Hard braking by running in reverse. Then forward. Notice how the braking sound stops when the car is speeding up in the same direction as the throttle input. Now I brake with handbrake input. Notice how the braking sound stops when the car is stopped, even though I'm still pressing the handbrake input. Okay, a smooth drive is easy. Let's see how well our system handles bumpy hills. Actually, this is more of a test for the physics engine than for the sound system. If the RPM is correct, then it will sound correct. Yeah, this chaos vehicle movement is really good. Though for racing games, I want the startup to delay a bit. Instead of starting to move nearly immediately on throttle, the engine needs to ramp up until it changes gears before moving. Forza and Need for Speed do it like that, which allows the synthesized sound to do a good RPM ramp up before moving. It will make the startup more impactful. Notice the output of our synthesizer a nearly stable RPM. Earlier I did tell you that granular synthesis isn't good with stable RPM. It is easy to check by running in reverse. In Forza, it sounds like this. That's the problem with granular synthesis. This is a very simple demo. We just use the default vehicle sample project that comes with Unreal 5. Then we added an audio component to the C++ vehicle pawn class like this. In the sport car blueprint, we set this to use the car graph. And in the tick function, we update the RPM, throttle, and brake inputs. Everything we use here can be easily extracted from any kind of vehicle engine physics. Because we allow reverse dwell to act like a brake, we do the logic like this. You might change the logic a bit if your game logic is different. We will release a build version of this demo and its source code when we update the plugin on the store. But it will take some time. I still want to allow the braking sound on heavy drifting. I didn't have much time with Chaos Vehicle Component, but I think that wouldn't be so hard, since it has steering information. Also, we need to add some tire scratching sound effects to make that braking more realistic. It's not hard, since we already have scratching synthesizers. Now, what can you do to customize this? Based on your vehicle's physics, you can add more inputs to this. For example, you can use the moving speed to increase the noise, to make it have more impact when driving at top speeds. What if your game supports a cockpit view? A cockpit is like a comp filter. So we can use this node again. A modal object with low and mid frequencies is good enough. Usually, wooden or plastic objects are good. Metallic and glass pitches are too high. Increase the decay to avoid resonance, which can make this very loud. Let's test this. You can feel that there is considerably less noise than before. It does sound like playing inside a box. Like I have said, convolution reverb. It sounds a bit more like a Lexus now. By the way, Lexus cars are very easy to model with our approach. They don't have much noise, and their harmonic focus heavily around the bass frequency. Granular synthesis usually has more noise compared to the real recording due to how they synthesize. And about our current roadmap, we will release the update to the store in 1 to 2 weeks. We need some time for more testing and fleshing out the demo. Version 1.2 will only have one car model. We will add more models for cars later. Some models for planes and motorbikes. Maybe some for boats and tanks too, if we can buy appropriate recordings for them. And that's it for now. I'll see you again on the next video soon.